So let's continue discussing the paging problem. In this previous example, the two seemingly best algorithms were the least frequently used and the LIFO. Now, it can be seen as a practice session, but we will first show that neither of them is competitive for any constant. So this can be a statement, for example. So neither of the LIFO and the least frequently used are competitive. This means that for each, say, k, for each number k, there is some input for which the algorithm's cost divided by the optimal cost is larger than k. So that's what it means to be not competitive at all, that this ratio is not bounded by any constant, but it diverges, it can tend towards infinity. So to prove these sort of things, we always construct the sequence of inputs and show that the ratio is divergent, so it just tends to infinite. So to do this, we explicitly give a sequence. So it will be a sequence, the first input sequence, the second input sequence, and so on, such that the algorithm's cost on these sequences divided by the optimal cost on these sequences tends towards infinite. If we just say move I to the infinite, and this is of course wrong in the mathematics setting, so it's just an equality sign. So we are just giving worse and worse and worse inputs in such a way that they can be arbitrary worse. So first let's deal with the LIFO because it's easier. So for the LIFO, there are options to do that. So set n to be k plus 1. So this is the least possible meaningful size for n, because if you have only k elements on the disk, then the whole disk fits into the cache, and after filling up the cache you won't spend anything. So this is the lowest possible value, meaningful value. And let's just first load the cache 1 to blah 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 k, and then k plus 1 arrives, and then say k arrives, and then say k plus 1 arrives, and then say k arrives again, and so on, and again k arrives, and again k plus 1 arrives. So let's just k plus 1, and this k plus 1 will say m times in total. right? So this is a block, this is a block, and so on, and this is the last block, the mth. So let's just denote this guy by sigma m. I'm not indexing with I, I'm indexing with m at this point, but it doesn't really matter. Now, so for the LIFO, what happens? So for the LIFO, okay, the cache is filled till this point. Then when k plus 1 arrives, it will just discard the k. And then when k arrives, it will just discard the k plus 1. And when k plus 1 arrives, it will just discard the k, and so on. It will spend unit cost for each possible request. So the LIFO's cost on sigma m, well, we have, okay, so there are k minus 1 inputs before these m times k plus 1 iterations, so it's just k minus 1 plus 2 times m. Okay, so I don't have to use parentheses here, so it's just 2 times m. Cool. So it pays for each request. Each request, since it discards always the one which just didn't get. But the optimal solution is much cheaper, since it's enough just to discard, say, the 1 instead. We can assume that k is always larger than 1 in all cases, because if you have a cache of size 1, then, well, basically you just have to discard that single element, and every algorithm is automatically optimal in that case. So for k equals 1, the online algorithms will produce optimal outputs as well. So it doesn't make any sense to study the problem for cache size equals 1. But if k is larger than 1, then if you just discard the 1, then this is a different element. So k is not 1. And then after that, everything is free, because k and k plus 1 are both present in the cache, which means that the optimal solution is something like k plus 1. Now, okay, this is just one solution, so this is just a lower bound at this point. It could be even smaller after just having this information, but since there are k plus 1 different elements in the input, then we have to spend at least k plus 1 cost for processing each of these. And the ratio, the LIFO divided by the ratio, is just this one, which is something which diverges to infinite if we just let m loose, because k is a constant, so this part here is just a constant, and this part is plus something divided by a positive constant, which just tends to infinite. So this is a very bad input for the LIFO, but it's not really a bad input for the least frequently used, because if you use the frequencies, then eventually you will just keep these two in the cache. Well, yeah. But there is another bad input for the least frequently used algorithm. So for the least frequently used, we also construct a bad enough input. And for the least frequently used, such a bad input can be 1, 1, blah blah blah. This is 1, say, m times. I'm just making this to get the LFU protect the ones, so if there is a large enough number of ones arriving in the beginning, then, well, in this case these guys won't get discarded at all, so it's m times again, and so on. and k minus 1 is also loaded m times, accessed m times, and loaded ones, of course. So at this point, each of these guys have a frequency of m at this point, and then k arrives, and then k plus 1 arrives, okay, and then k arrives, and then k plus 1 arrives, and so on. Again, I'll do this k and say k plus 1 m times, so it's just this part is m times. Because what happens, the least frequently used algorithm will just have at this point, it will pay k minus 1 till this point, and then we have the 1 m times, the 2 m times, and so on, the k minus 1 m times, if we use the frequency counting as an upper index, as a superscript. And then I'm just loading the k, which is good, okay, and then when I'm loading the k plus 1, I'm just dropping this k and count, and then I'm just loading the k and drop the k plus 1, and still the counter resets at 1, and then I'm discarding this guy and loading. So that version of the least frequently used algorithm is just behaving exactly the same way as the LIFO as soon as these guys have enough occurrences. So the algorithm's cost on this particular input is k minus 1 plus 2m again. Now, if we manage a global counter, which I told you not to be very efficient and not to be very plausible, but still we can do that. So the global variant will also discard this guy, because if you just load k, it will have the in first occurrence superscript 1, which is smaller than m, so k plus 1 will nevertheless discard this guy, and k plus 1 will have a superscript of 1. And then this k will discard the k plus 1, even if you have a global counter for each possible page in the memory, then you will go to k2 at that point. So since 2 is smaller than, if 2 is smaller than m, then we will discard the k instead of all the others, because the others were loaded very frequently in the beginning. So then you will get to k plus 1 second time, and then the k to the third time, and so on. But still, even the global version will discard k plus 1, k plus 1, k plus 1. So that's a bad input, because again the optimal solution would discard at this point the 1. And then, since both k and k plus 1 are members in the cache, we won't pay anything for this part. So this is again k plus 1, and again the ratio is something like this, which tends to infinite if we get m loose, if we let m loose. So basically this means that these two algorithms behave well on that particular input which we've seen, but they are not competitive in general, which might be surprising, but it's easy to construct a bad enough input to such an algorithm. It's almost always. So neither LIFO nor LFU are competitive. Now we will see that LRU and FIFO are both competitive algorithms, but first I will try to prove a bound for the possible competitive ratio of a deterministic algorithm. So I'm just zooming here.